Sorry, I think I was wrong in what I said at the beginning. Actually, this is not the fourth presentation, but it's the fifth one. So it's the last one, which is going to replace the third one, which has been cancelled. So this presentation is actually a very international collaboration coming from France, England, and Canada, I understand. And Jerome and Nicolas is going to give the presentation. Thank you.
Thank you. Sorry. So this work is called Washboard, and indeed it's a collaboration between myself and Florence Bitbol, who was a student here, and Jim McIlway in Cambridge, and Stephen Morris from Toronto. Apologies to those of you who's heard this many times already. So let's start with a picture of a typical washboard road. This is a picture taken in the Australian outback. And this is what they call a dirt road, so it's a road made of either sand or gravels. And as cars and trucks or lorries drive on this road, you do see this little pattern here, quite regular, forming small ripples. So typically they're about 30 centimeters in wavelength, about, let's say, a few centimeters in height, and they form after, well, let's say 100 or thousands of cars have passed on the road. So we like to think of that as instability of flat granular surfaces under the action of rolling wheels. So as an introduction, I first want to say that this phenomenon is of course well known in engineering, but the engineers of course are interested in a system that mimics a car suspension. So there's a dashboard, there's damping, of course, rather than being interested in the physics behind it. Of course, this phenomenon has some relation to other rippling instabilities, such as beach ripples or wind ripples, but it also can involve other types of deformation, such as wear, plastic deformation, or, in the case of sand, material transport. So this is a picture of what they call a streetcar in Toronto, and this is a closer view of the rail track of the streetcar. And you do see, of course, it's not on the same scale as on the road. This is something like 5 centimeters in wavelength, but this system does develop nice ripples. And this is because they don't take good care of their ripples. Whereas on trains, or train tracks, they tend to pay better attention to the trail, well, to the track. There is some relationship also to ski moguls on the ski slope, although, well, in this case, there's a suspension. It's your knees and your legs. But there are other differences, of course. In this case, compaction can be very important, and the pattern is fully 3D, as you can see. But mostly this is to mention the nice paper here. All right, so we have two experimental systems, one in Cambridge and one in Lyon. So in real life, vehicle suspensions consist of deformable tires, they have spring, there's a dashboard. Different vehicles, different cars have different masses, different wheel size, different everything you can think of, velocity. But as physicists, of course, we want to reduce the number of parameters and understand the fundamental mechanisms behind the formation of those ripples. So we have one experiment here in which the table itself rotates at something like half a hertz. It's 1 meter in diameter, and the wheel, you can sort of see it here, is simply attached to an arm. It's free to roll on itself, and free to move vertically as well. In the other experiment, there's a circular track filled with sand, and the arm rotates around the track again at a given velocity. This one is a bit larger, it's 2 meters in diameter. So both systems have advantages. So the first result is that it works, and actually it's extremely easy to obtain ripples in the lab. So if the velocity is high enough, so this is a closer picture of the wheel. If the velocity is high enough, after a few rotations, typically 10 or 20 or 50 rotations, the ripples start forming at a random position where there was some perturbation, some initial perturbation. They rapidly grow and they spread to the whole table. And I should emphasize here that because of the nature of our system, the wavelength in a steady state has to be quantized. However, we think that the perimeter of the track is large enough so that this is not really a big problem for us. So in other words, we have several wavelengths around the track. We also have a nice laser scanner that allows us to obtain very accurate measurements of the bed profile. So we can record the bed profile, and we follow the position, the vertical position of the wheel with an angular sensor. And by doing this, at the same time, we can compute the trajectory of the wheel and superimpose it to the bed profile. And this is a typical trajectory. So what's interesting to see, well, there are a few things that should be noticed. First of all, the wheel does take off at the crest of each ripple. So this is a typical trajectory, but this is not always the case. At lower velocities or at initial times, the ripples can exist, although the wheel seems, at least, does remain in contact with the bed. Something else that should be noticed is that the profile is not symmetrical, as can be clearly seen here. And this is, again, very close to what is seen on ripples or on dunes. So this is a space-time plot of the vertical position of the wheel, which is related, not identical, but very closely related to the profile of the sand itself, of the road. So this is the angular position from 0 to 360 degrees, so this point is the same as here. And this is time measured in number of rotations. The colors here simply represent the height of the wheel. So you do see that we start from a completely flat surface. And as time passes, well, ripples appear at some point, some random points, say here, and they rapidly grow in height and in length, and they spread to the whole table. You can see that within 50 rotations, the whole table is covered in ripples. So there are also merging events between a few ripples. Of course, you start here with something like 15 ripples, and after 500 rotations, you end up with maybe, 8 ripples. So a few ripples have disappeared. They've actually merged together. And this is those events that you can see here. And I'm not going to talk much about that, but I want to say that those are complex events, and they don't simply imply two neighboring ripples that would merge together. But you do see that pretty much all ripples are involved in the merging or in the birth, that's rare, of a ripple. Something else that should be noted here is that the ripples do travel along the road. You do see that all those lines go, well, in the direction of traffic, right? Okay. So we also performed DEM simulations. In this case, the system is purely 2D. It's periodic as well. This is only a fourth, I believe, or fifth of the total length of the simulation, because again, we didn't want it to be too quantized. In the simulation, the bed here is made slightly polydispersed to avoid crystallization. The wheel is free to move vertically, it's free to spin, and there's no torque applied. So this is an important difference with a car as well, in which the torque does make the car move. Here, it's simply dragged at a constant velocity. And as you can see, the ripples form and do, at least visually, resemble the experiments. So again, it shows, well, it seems to show that this phenomenon is very robust. It didn't take us long to either obtain it in the experiments or in the simulations, so that's an indication that, well, ripples are easy to obtain and not easy to get rid of. This is a space-time plot of the bed profile in the simulation, and as you can see, it's very similar to that of the experiments. The ripples grow in height, they grow in length all the time, they merge, they travel along the road in the direction of traffic. Voila. So the simulations are interesting because, first of all, they tell us that humidity is not a problem, static electricity is not a problem, that indeed having a fully or only 2D simulation does reproduce ripples, but we can also measure other things in the simulations, of course. So in this case, the grains are colored by size. The small grains appear in blue, the larger grains appear in red, and you don't see any clear trend. Maybe you would see, you can see little clusters, but there's no such thing as a large-scale segregation. It has been suggested to us that maybe the smaller grains will form the ripple itself, or the larger grains will. Well, this is not the case. I'm not saying that if we tried a wider range of sizes, we wouldn't see segregation. But segregation is not key to the formation of ripples. The same is true for compaction. So we've computed here the local packing fraction for individual grains. So where the packing is loose, it appears in light blue, and where the packing is rather dense, it appears in red. And again, there's no clear trend. So the same conclusion holds. Compaction may occur, but it's not a key element for the formation of ripples. It may be important in the case of snow, but for grains, it doesn't seem to be very important. We can do all sorts of other things as well, such as measure the displacements between two consecutive passes of the wheel. It seems to show that the ripples travel on a static bed, and this is just to show that we can do anything we want with the simulation, of course. So we can now wonder what influences the pattern. Well, the first obvious parameter is the velocity. I didn't mention that earlier, but there is a critical velocity below which the bed will remain completely flat, and if you try to perturbate it by making a bump or a little hole, it will simply erase everything you try to impose. And above that critical velocity, the ripples will appear. Can take time if you've prepared if the road has been well prepared, it's extremely flat, it will take time. Can take 500 or 1,000 rotations, but eventually it will appear. And if you perturbate it, they start right away. So the velocity is obviously a very, very important parameter. And above that critical velocity, the ripples increase in height and in length with increasing velocity. The density of the grains seems to affect the critical velocity as well. We've tried with rice, we've tried with couscous, we've tried with sand. So of course, it's maybe too much for me to say that the density itself is important because the shape changes. But we are convinced that it's the case. The mass of the wheel, or the mass that the wheel supports, I should say, has a strong influence as well, and this is just a little example of that. You have a test run here, so this is a space-time plot again, position versus time. And adding extra weight, you do see that it changes pretty much everything. It changes the drift velocity, it changes the amplitude, it changes the wavelength. What's even more interesting, maybe, it's what has no influence on the pattern. So we've seen that the depth of the sand bed has no influence as long as there's enough. Of course, if you put just 2 layers of grains, you will run into problems, but otherwise that's not an issue. We've tried to double the depth and it didn't change anything. Also, very interestingly, we obtain an identical pattern with a blocked wheel. Jim always says that because we work in a math department, we thought it'd be a good idea to try with a square wheel. And you do see a square wheel here. So it's not actually even a wheel because it's blocked, it can't roll. But we do obtain nice ripples with a blocked wheel or even with a square wheel. So this is very interesting because it means that the wheel, or I should say rather, we call this a plow, that the plow diameter or the plow size has no influence. The system only feels the tip of the plow and has no idea how big it is. It can only feel the weight of the plow. So this is very interesting because there's no characteristic length. To our great surprise, I must say also, we obtain exactly the same pattern with grains of different sizes. So this is a picture on the same scale of 2 grains, 2 natural sands, and we obtain exactly the same wavelength and the same amplitude. So the grain size does not seem to be a relevant parameter. Again, if you tried with boulders the size of the wheel, you will have problems, but within reason, the size of the grains should not affect anything. So as I said, we use the plow, and this is a picture showing that with the plow, it does work very nicely. It is a lot simpler than a wheel because there's no rotation and there's no characteristic length in the plow. Well, there's a width, of course, but as we've seen, we believe that there's, well, more than believe, we proved that the system is essentially 2D. So we can try to think of scaling laws. We've shown that the grain size or the size of the plow are not relevant parameters. So there are only 4 relevant parameters left. The mass of the wheel, which has a strong influence on the pattern, the density of the bed, rho, the velocity of the wheel, and gravity, of course. So maybe I shouldn't mention those 2 lengths here. But doing this, there's only one way to construct a dimensionless number which controls this instability, and it's the following form, v squared over g times root square of rho over m. We call that a Froude number because there's a tendency for all of us to call any dimensionless number a Froude number. So sorry for not being more creative than this. So this is our Froude number, v squared over g times root square of rho over m. So if indeed we are right and there's one dimensionless number, it should control the instability. In other words, the transition from flat to washboard, that is the critical velocity, should occur at a constant Froude number. If the Froude number is constant and the sand is kept the same, gravity is the same, of course, v squared should scale as root square of m. In other words, the critical velocity should scale as a 1/4 power of the mass. And indeed, those are experiments that we've performed. So changing the mass, adding extra weights on the plow. So this is for a plow. The red dots here correspond to a bed that remains flat, whatever you try to do. And the squares, the black squares, correspond to the formation of a washboard pattern. And indeed, you do see that this line is well fitted by a 1/4 power law. So this, in our opinion, validates the proposed scaling. And just to show you that I'm not cheating here, it's the same data on the log-log plot. Well, v squared as function of root square of m, and you do see a nice straight line. So I'm just going to try, let's see if that works. Nope, come back. To show you synchronized movies. So what we've done here is taking a picture at every rotation. So in the first movie, you will not see, the first movie was taken for a plow, and you will not see the plow. But I'll show you if, well, hopefully you will see the movie itself. Nope, no luck. No, it's playing, it's not loading.
If you switch it to, if you switch it so you can't see it on your screen, then you should see it on the...
All right, good, that's good advice.
Much clearer now.
It's coming, it's coming.
So you can't see it on your laptop?
I can't see anything, that's right. Thanks, Nico. All right, so in this experiment, the plow actually goes this way, right? And this is a picture taken at every rotation. So as you did see, we start from a flat bed, and you do obtain very nice ripples. So in this case, well, this corresponds to, I believe, 500 rotations or 1,000 rotations. You do see ripples appear, they grow in time. You do see those strange waves propagating, which correspond to merging events of 2 ripples, well, the disappearance, I should say, of 1 ripple. And it seems to have reached a pretty steady state. So let me play the same movie, but faster. So this is exactly the same data. Okay, and here you do see those nice waves that travel faster than the ripples themselves. Okay.
Are the ripples moving through a front ripple?
Yes, you will see that. I'll show that just in a second. Okay, now let me try to show you movies with the wheel. So sorry, but it's in the other experiment and the wheel's going the other direction. So in this case, let's go. The wheel, as you can clearly see here, will go this way, right? But you will not see it moving because the picture was taken at every rotation. All right, all of a sudden the ripples appear and they do move along the road in the direction of traffic. You can see them pushing one another, sort of. Okay. So in this case, they are less 2D. There's more of a 3D pattern, but this is because the wheel itself is narrow, it's quite narrow. let me try to show another one. So this is changing the velocity. This is actually faster than the previous one. It's not starting. Let's do that. All right. So you do see them going faster. You can see that the wavelength and the size of the ripples themselves is larger than in the case of a slower wheel.
So the wheel is jumping here.
It's jumping. It definitely jumps here. But it's not always the case. This is a relatively fast wheel. Okay. So this is a full space-time plot of the typical space-time plots obtained with the plow. Again, starting from a flat surface, which you can't really see here. So this is in hours. Maybe it's not the proper unit, but that corresponds to roughly 5,000 rotations. And you do see that there is some evolution over a very long time. So this is only 2.5 hours, but this shows the amplitude, the maximum and minimum amplitude over 20 hours or 24 hours. And you do see that, well, it seems to have reached a steady state, and it stays happy in the steady states for maybe 10 hours or more, and all of a sudden, something else happens. So we can also compute Fourier modes. We can make a Fourier transform of the signal here, and again, plot that over time. And you do see that it's maybe a mess, but it's very interesting. Well, indeed, for maybe between 5 and 10 hours or 5 and 15 hours, it's happy, and there's one mode here that dominates the system. But all of a sudden, maybe not out of nowhere because you see it growing, there's another mode that appears. So it's very difficult to claim that we've reached a steady state, although we can obtain steady states that are steady for days, and then all of a sudden, after 1 week, one new mode will appear. So this is a rather steady state, but again, that's only over half an hour, so maybe something like 1,000 rotations. So it seems to be very stable. There's only one Fourier mode, but we can also obtain nice patterns here with 2 modes that are completely superimposed. And this is what you were talking about. You can think of that as a wave, a smaller wave traveling faster than the ripples themselves and going through the ripples. But it's almost the same as thinking of a line of balls bumping into each other, you know. All right, do you have a few minutes? Just a couple of minutes. So one important thing is that the experiment is running in a building next door. So if any of you is interested in seeing it, Jim and I would be very happy to show it to you. So if I have a few minutes, I'll just come back to my conclusions. I want to say this. So we've obtained scaling laws through dimensional analysis. However, the Froude number can be seen in terms of the ratio of 2 lengths. And I'm not going to go into too much details, but if now, so the scaling law I showed to you was for the plow. But using a wheel, there is now a new length, which is obviously the radius, or the diameter of the wheel. And, well, we've convinced ourselves, and I think it's pretty convincing, that the velocity, critical velocity in this case, should scale as a 1/6 power of the mass. So these are experiments done with the wheel, which is blocked, okay? It cannot roll. It's simply dragged and blocked on the surface, and it does develop very nice ripples. If a plow does, a wheel should. And indeed, if you, well, this is this is only over less than 1 decade, so it's maybe too much to argue or to claim that we've found a 1/6 power law, but let's just say that the 1/6 power law is compatible with this idea, and 1/4 does not work. If you try best fit here, it gives 0.19, which is closer to 1/6 than 1/4, but it'd be maybe too much to claim that it is clearly a 1/6 power law. However, if you now let the wheel roll on the surface, the dependence of the velocity, the critical velocity on the mass, is a lot weaker. And this is the data on the log-log scale. This is a 1/6 power law, and you do see that it miserably fails. So in this case, of course, there's something else which is very important. It's the moment of inertia of the wheel. And the mass that it supports is not the only relevant parameter, right? If you have a wheel that's twice as big, or a smaller wheel that supports some weight, these are very different situations. So we should try to take this into account in our model. So let me just show you the conclusions. I just want to repeat here that washboard roads exist with a very simple system. This is not obvious. A lot of people, there's a misconception that it's due to the suspension of a car. So we obtain that with no torque applied onto the wheel, with no spring, no dashboard, with simply a plow or a blocked wheel. So it's a very robust phenomenon. It exists in experiments or in simulations with small, large grains, wet or dry, with the sand or with rice, with a wheel that's not spinning. We showed that size segregation or compaction are not responsible for the instability, that there is a critical velocity. We don't know why there should be a critical velocity yet, but we found a power law that explains how it scales with the mass. And you can see nice pictures here on this webpage, and we've published something if you're interested. So thank you for your attention.
Will you long-term transition after 20 hours, I guess you say, or something like that? Are you sure that there is no external
No.
way to say, did you control your rotating table with a seismometer or so?
We have controlled the rotation speed, but we fully agree with you, and this is why we have also the other experiment. We haven't run the other experiment for hours and hours, but we are very concerned that the transition over 24 hours may be due
Car
to
may have passed.
anything, or the weather change, or
Custodians.
absolutely.
Right.
Are you interested in times as long as 24 hours? That would correspond to about 50,000 cars.
Yes.
These roads don't have that much traffic.
Well, I would have agreed with you, but I was told that in Australia, the Australian government used to take care of those roads. Basically what they did is just to run down, to erase everything they saw with bulldozers. And they stopped doing this because it would come back the next week, the following week. So I would say now that they've stopped doing this. It's not, it may be true that 5 million cars will drive on that over 10 years. Or if they stop scraping the ripples, it may be true. But I agree with you, it's more out of scientific curiosity than practical interests.
You talked a lot about the scaling of the critical velocity. There are two other obvious parameters, which are the length scale of the ripples and the velocity of the ripples. And I was wondering how those connect to your basic dimensional length scales and your Fruta number.
We have not done much work on this, but this is a plot of the wavelength as function of the Fruta number, and you do see a nice power law. So I'm not going to comment too much on this because these are still something we're working on. And this is in what we believe to be a sort of steady state. So again, that's why I didn't talk about it too much. However, there is clearly an initial wavelength, because the ripple starts from a zero amplitude, but they don't start from a zero wavelength. And this we haven't looked at yet, but we are very interested in doing this. However, this is the data that we've taken, so it seems to show that the wavelength scales as b squared over g, which is simply a ballistic length. But this ought to be more complicated than this.
Is that L? Is that an L or is this square root of an L?
Sorry?
Sorry, I'm a little confused by the dimensions, but I can ask you privately.
Okay, sure.
Just the last one.
I've got a real practical interest in this because I've driven on washboard roads in many stage rallies,
Yes.
and often before a stage rally, the stage is planed, and you see these washboard sections emerge after the passage of even sort of 10 or 20 cars. You tend to see them most often starting off in acceleration zones after corners,
Yeah.
and I wonder whether the natural tendency to axle tramp under acceleration, where you get stored energy exchanging between the tyre and the suspension spring, may be contributing towards the initiation of this.
It may be. I can only say that it's not necessary to accelerate to obtain the ripples. All those were done at constant velocity. But you're right in the sense that accelerating may create the initial perturbation. And this may be why the ripples would start here
quickly.
rather than elsewhere on the road. But they should appear everywhere on the road. And actually, in experiment around the track, there are usually 1 or 2 or 3 spots at which they start. It's not just where there's not one starting point. It's form ripples here, and further down the road, will form ripples maybe 10 rotations later. So I do agree with you. And we've been told also that it appears a lot when the road goes uphill or after a sharp turn. And I believe again that this is maybe just a cause of initial perturbation rather than something more fundamental about acceleration.
Okay, thank you again, Howard.